Okay, let's continue. We will do 11.6 today. Now, among all these series that we dealt with, alternating series is the easiest, right? You just need to show that it is actually the positive part, or the absolute part is actually it's alternating, and then it's the absolute value is actually decreasing down to 0. Okay, and to be honest with you, all you need is eventually decreasing. Okay, that's what you need. Yeah, that's what you need, eventually decreasing. Now, 11.6, we have some new definition. This is on absolute value, absolute convergence. That's the first part. The second part, ratio test. And then root test. The first one, absolute convergence. In the previous section, we then start dealing with sequence, a series whose terms may be positive, may be negative. Now, prior to that, maybe I write it down in kind of like a side note. So in 11.2, 11.3, we dealt with the series where the terms is non-negative, right? Okay, and then in 11 point, is it including 11.4? I think it's including 11.4. Yeah, and then in 11.5, we then deal with alternating series. Okay, doesn't matter that one. And the Bn is the positive part, the non-negative part, right? So originally we dealt with positive terms, and then in 11.5 we deal with maybe positive, maybe negative. Now, what is absolute convergence? Absolute convergence is the following: series sum of a sub n is absolutely convergent if the sum of the absolute value of the terms is convergent. Okay, that's the definition. That's the definition. Absolutely convergent. It's absolutely convergent if you place absolute value on the terms in the series. Okay, and it is convergent. Now, so with that said, then that's the definition, right? That's the definition. Then consequently, okay, the series with positive terms is convergent and absolutely convergent at the same time. Is that right? Well, because if the terms a sub n is positive, then a sub n, the n term, is equals to the absolute of n term. So the sum of that series will be the sum of the absolute values, right? Okay. Does it make sense? Now, why do I say so? So here's the thing. Later, you will see we apply that ratio test and root test. Can be used for absolute convergence. Okay, it's actually the root ratio test. Root test is actually for absolute convergence. Okay, but and if the terms is positive, then it will be convergent too. If that one is actually kind of a bit hard to explain. And if the terms is positive, non-negative, then it implies convergent. Okay. In fact, it is true if, maybe I say it another way. Also note that if a series is absolutely convergent, then the same series is convergent. What's the proof? What's the proof? Here's the proof. We know that A1 plus A2 is less than equal to the absolute of A1 plus A2 is less than equal to absolute of A1 plus absolute of A2. And by induction, we can go forever that the absolute of, by induction, the absolute of the series is less than equals to the series of the absolute. Okay. Now, of course, the left-hand side here is bounded below by 0. Right? It's bounded below by 0. Therefore, if this is convergent, which means that's equals to some constant here, then this guy here will also be convergent. Okay, so absolute convergence is actually a situation that a lot stronger than regular convergence. Okay, absolute convergence is stronger than regular convergence. Okay, so if this is convergent, then this guy here will also be convergent, right? Okay, so absolute convergency implies the regular convergency. Now, then you see we have the following situation. There's a absolute convergence is the strongest. Not so strong is just convergence. Okay, so there could be, there are series, there's a situation that the series that a series is convergence, but not absolutely convergent. Okay, you can see that as if we have the following. So if I have a Venn diagram, okay, this is convergence. Okay, inside that you have absolutely convergence. This is what I mean. Once it is absolutely convergent, it must be convergent. But you may have series that is convergent, but not absolutely convergent. Okay? Okay? Now, that's the layer. That's the layer. One classic series that is not absolutely convergent yet convergent is alternating harmonic series. Alternating harmonic series is convergent but not absolutely convergent. That situation is called conditionally convergent. Conditionally alternate harmonic series is the sum from 1 to infinity of -1 to the n minus 1 of 1 over n. I hope you still remember that. Okay, now we have shown that this is convergent. We have shown that in 11.5. Where what we need is that the sequence is decreasing and then the limit is 0, right? Okay, as long as it is alternating, then we just need the sequence to be decreasing down to 0. Okay, now, however, the series of the absolute value which will give us the harmonic series, we have shown that to be divergent. Okay, now that's what we call conditionally convergent. Now, you can see, for example, another example, suppose I do this one here. The series of, let's say, -1 to the n of 1 over n squared. You can see, you need to show this yourself. Okay, now you will see that, if I apply the absolute value, we get a P series. That's P series P equals to 2, which is greater than 1. Right? Okay, so this is convergent. So what happened to this series? Then we say the series that we originally supposed to talk about is absolutely convergent. Okay, and because it is absolutely convergent, then of course it is convergent. Now, how do we use this? How do we use this? We can use this absolute convergence to help us finding the convergence of series whose term is not always alternating, but sometimes positive, sometimes negative. Now, for example, the one I see in our textbook is this one, cosine n over n squared. Now, cosine 1 is positive, cosine 2 is negative, cosine 3 is still negative. Okay, cosine 4 is still negative. So it's not precisely alternating, it's not plus minus plus minus. Cosine 1 is positive, cosine 2 is negative, cosine 3 still negative, cosine 4 still negative. I think cosine 5 is positive, maybe. So there's no certain pattern when it is positive, when it is negative. Now, however, we can do the following. If I need to see if it is convergent or not, what I can do is attack that from absolute convergence point of view. Okay, consider the series of the absolute value. Okay, now then I want to say that this is less than equals to the series of 1 over n squared. Is it okay? Now, we say that, note, this series here is convergent by what's the reason this series is convergent?
P series.
Yeah, P series, P
By
equals
series, by P series, P equals to 2, which is greater than 1. Okay, so by what reason I will say that this series is convergent?
Comparison test?
That's right, by comparison test. Okay, it's bounded above by something convergent, and the terms is positive. Now then, because this is convergent by comparison test, then what can you say about this series?
That series is convergent.
Before I say it's convergent, it is absolutely convergent first.
Oh, right.
Right? Okay. and therefore that series is convergent. Now, it is a standard that once I can show that it is absolutely convergent, it is also convergent. Okay, so the last sentence is actually not really necessary, but I just want to make it clear for you that if you want to find out if a series is convergent, one way to attack that is by seeing the absolute convergence. Okay, now, but on the other hand, simply because it is not absolutely convergent doesn't mean it is divergent. Okay, because if you look at this diagram here, simply because it is not in absolute convergence, okay, doesn't mean it is outside. Doesn't mean it is divergent. No, that's not true. It is possible the series is convergent, okay? It's just not absolutely convergent. You see what I mean? It is possible you have a situation where it is conditionally convergent. So if you check the absolute convergence, it turns out to be not absolutely convergent, you cannot say that it is divergent. Okay? Now let's see problems in our book. Let's say we do number, you want to choose a problem? Maybe number 4? Or number 14? Let's do number 4 first then.
Professor, I just have a quick question.
Mhm.
So for when we compared cosine of n over n squared, the absolute value of that to 1 over n squared, do you want us to still prove why we can do that with like cosine n is always greater than -1 or less than -1?
Actually, you just need to show that cosine n is the absolute is always less than or equal to 1.
Okay.
Yeah, it comes from the fact that you just said. But that fact is way too far earlier before this calculus 2. So we can just, you don't even need to show this anymore.
Okay.
This is something we consider a fact.
Okay.
Okay? Yeah, that's something
Thank
we
you.
consider a fact. Now, so for example, we have this. For example, we have the summation of -1 to the n. Oh, hold on, I'm looking at the wrong question. To the n minus 1. I was in 11.7. And then n over n squared plus 4 from n equals to 1 to infinity. Okay. Now we have 3 layers. It's either divergent, conditionally convergent, or absolutely convergent. Okay. We have these three things. Okay. Now, if you think it's divergent, you try to prove it's divergent. If you think it's absolutely convergent, you try to prove it's absolutely convergent. If it is conditionally convergent, you need to show that it is not either one of these two. Also, to show that it is absolutely conditionally convergent, then you need to show that it is not divergent and not absolutely convergent. You see what I mean? That's how we show that it's conditionally convergent. Okay. Now the thing is that when we see a problem, let me write it here. When we see a problem, we actually don't know is it divergent, absolutely convergent, or conditionally convergent. Okay. So use your instinct. For example, in this case here, this is the alternator, right? And this is the positive term. Are you with me? Okay. So I want to show, oh, you know what? This is alternating, right? This is alternating. Is it right? Alternating, and it's apparently that's actually going down to 0. So I will say the following. Okay, let Bn be the positive part. Okay, I need to show, I claim that Bn is decreasing. Proof. How do you prove that this term is decreasing?
You can show that Bn plus 1 is less than or equal to
Okay, so
some Bn.
So let me do it aside then. First, n plus 1 over n plus 1 squared plus 4. I need to show this, but for that to happen, I need to have n squared times, I'm sorry, n squared plus 4 times n plus 1 is less than equals to n times n plus 1 squared plus 4. That seems to be a lot to do. I honestly don't really want to do that. Okay, plus n squared here plus 4n plus 1 less than equals to, this is n times, that's n squared plus 2n plus 1 plus 4. Okay, so this is n cubed plus n squared plus 4n plus 1. On the right hand side I get n cubed plus 2n squared plus 5n. N cubed cancels, n squared cancel. So 1 is less than equals to n squared plus n. Right? Okay, now the thing is, for this to be true, I need to start from here. This is my scratch work, by the way. Okay, so I suppose to first say that 1 is less than equals to n squared plus n. Therefore, this is the art of proving this thing. Less than equals to n cubed plus 2n squared plus 5n. Okay, and then I factor these. Did I factor this right? Actually, this is 4. Huh? This is 4. This is 4. So this is not always true, though.
Yeah.
Right? This is only true for n greater or equals to 2. Right, but that's okay. The first term doesn't change. The first term doesn't change the convergence, right? Okay, and then I go on further. When I factor, this is n squared plus 4 times n plus 1. This is n times n plus 1 squared plus 4. And then therefore n plus 1 over n plus 1 squared plus 4 is less than equals to n over n squared plus 4. Bn plus 1 is less than equals to Bn. Okay, so this is actually, of course, the best way, but suppose you don't like that. I mean, you already did this, right? Okay, now if you want to argue this way, the one on the right hand side, if you want to argue on the right using the one on the right hand side, let me use this notation. So there are two groups. If you want to use the one on the right hand side, you're still okay, but you need to put this notation here. This notation is if and only if. Okay, as if you are saying that Bn plus 1 is less than equals to Bn, is true if and only 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 if for n greater equals to 2. Are you with me? So to prove this first claim here that Bn is decreasing, the first way is, the best way is the first way, method 1. Okay. Or you can use this method 2. But you need to make sure that you use this notation. Okay, make sure you use this notation. What's wrong if I don't use that notation, Thomas? What's wrong if I don't use that notation? If you don't use that notation, mathematically speaking, what it means is this implies this. Okay? Implies this, implies this, implies this. Now that's why in our method 1, I don't need to use that if and only if notation, because what I want to show is this. That's what I want to show. Okay? Now, the thing is in our method 2, this is what I want to show, right? I want to claim that this is true. Okay? But for this to be true, this has to be true. 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 This has to be true in this situation. And there's no contradiction. Okay? This is what I want to prove. Okay? This is what I want to prove. But for this to happen, okay, for this to happen, you need to have all this happen. Now, at the end here, you want to show that this is true just by instinct or by just looking at that. Okay, something that clear for everyone to see. Okay? Are you following me? There's a proving called deduction and induction. Okay, the one on the left-hand side, you can call that deduction method. Okay, in which I start from something we already know, everybody can agree, and then I've developed that to get what I need. Okay, now method 2 is in some sense is induction. In some sense is induction. This is what I want to prove. Okay, but this is true if and only if this is true, 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 but we know this is true. Therefore, the original one must be true. Okay, now if you have that situation, you need to use this if and only if notation. Okay, by the way, do you have idea on the third method to show that Bn is decreasing?
You let it equal a function and then take the derivative.
Derivative.
Yeah, that's right. So we use the continuous superposition function. Okay, so let fx equals to what's that thing? N over square root of n plus 4, right? Oh no, x, sorry, not n. And note that fn is the Bn, okay, and then you show that f prime x. I think this one in this case is easier, right? Because the denominator will always be strictly positive. Okay, the numerator will be x squared plus 4 minus x times 2x. That's 4 minus x squared over x squared plus 4 squared. This is negative for x greater equals to 3. I use 3. It can be any number. Just make sure that from 3 and on, it's negative. Okay. So f dx is decreasing, therefore the positive term ds also bn is also decreasing. So implicitly, I reinforce again how to show a sequence is decreasing. Okay, and then I need to claim another thing. What else? Claim that the Bn is convergent to 0. Okay, so n over n squared plus 4. I will divide the top and the bottom by n. That's equals to 1 over n plus 4 over n. This convergent to 1 over, that's basically 1 over infinity. Let me divide by n squared. What am I doing? Let me divide by n squared. This is 1 here. So this is 0. It's convergent to 0 over 1 plus 0, which is 0, as n goes to infinity. Okay, so by alternating series test, this series here is convergent. Okay, but we still don't answer that question though. We still don't answer that question. Okay, is it, well, by knowing that it's convergent, it's not this one, but it's still either conditional or absolute. Okay, yeah, it's either conditional or absolute. So let's go further. Test the absolute. Now consider the series of absolute values, which is, oops, the sum of -1, is it to the n or n plus 1? N minus 1. Put absolute sign. Boom. So this is equals to n, the series of n over n squared plus 4. Do you think this is convergent or divergent?
Divergent.
Why?
I feel like in the end it's gonna be harmonic.
Yeah.
How do you show that it is quote unquote harmonic? What test will you use?
Use the comparison test.
Use comparison test? Okay. So, oh, comparison test, I don't think so. How do you use comparison test?
You could say it's less than or equal to n over n squared.
Hold on. I need to use red color because that's not true. Okay, let's see. Yeah, let's see the flaw of. No. It's what you say is true, but there will be a flaw in the logic, because it is true that this is less than this series, right? That's what you want to say.
Yeah.
And you argue that this is divergent. Okay, but if you bound it above by something divergent, you cannot say this is divergent.
Yeah, the only thing you could do is the limit
If you bound it
test.
below, if you bound it below by something divergent,
Okay.
then it is divergent, right? Bounding it above doesn't tell us anything though. So it is true that it is greater than, but nothing you can get from there.
Right on.
Okay. So what is the other test you say? we know it will behave like harmonic, but not bound by bounding it above. So let's try limit comparison test. Okay, compare to harmonic series. That is that. The limit n goes to infinity of n over n squared plus 4 big over 1 over n is equal to n squared over n squared plus 4, and then that's equals to limit n goes to infinity of 1 over 1 plus 4 over n squared. I cannot use L'Hopital rule, that's why I just divide by n squared, and this is equal to 1. Okay, which is finite and positive. Okay, so by limit comparison test, this series here is divergent. But what is the reason we show that's divergent?
We want
To
to
show it's not absolutely
So
convergent.
this series is divergent. So the work is long, huh?
Yeah, I got to prove a lot.
Yeah, you basically need to prove two things. If it is absolute, if it is conditionally convergent, you need to show two things. It's this one but not that. It's this one but not this. Okay, is divergent. So the series itself, the original series, the alternating original series, is conditionally convergent. Okay. Now, do you want to pick any question from here? I did number 4, so you have choice number 6 up to maybe choose the one with alternating though. Even though I still need to teach you the root test, ratio test, and root test. Number 12, let me do it here so that I don't take too much space. Number 12, the series of sine 4n over 4 to the n. I think this is absolutely convergent. Yeah, because the top one is at most 1, right? So, solution. Consider this series here. So that's the series of the absolute value. Now this is less than equal to the series of 1 over 4 to the n. Right? Now then this series 1 over 4 to the n, is it convergent or divergent? I hope you know why I picked that one. This is convergent because
absolute value of r is less than 1.
By geometric series, absolute of r, which is equals to 1, 4 is less than 1. Okay. So What is the reason that this is convergent?
It's bound above.
We have no such test.
The comparison test?
By comparison. So you are actually right. You go to the right direction that it is bounded above. Okay. But the test that we use to claim that it is convergent is comparison test.
It has to be explicitly stated.
Yes.
Okay. Okay.
No, but the series of the absolute value is convergent. So what happened to the original series? What can we say about that original series?
It's absolutely convergent.
It's absolutely convergent. Okay. Now, from here to here, it's really just by definition of absolute convergence. Definition of absolute convergence is if the series of the absolute value is convergent, then the series without the absolute value is absolutely convergent. Okay, this is just by definition, which we usually don't say anything if it is just by definition. Okay, now let me go on with the other two tests and go back to do some problems. Okay, I will state the test without proof. Ratio test. Okay. What is ratio test? Ratio test says the following. If a sub n plus 1 over a sub n converges to an L, okay, then the series I think I need to put absolute sign here, sorry. The series is convergent if L is less than 1. It is divergent if the L, the limit is greater than 1. Inconclusive if L is equal to 1. Okay, now suppose the ratio is convergent to L. What happens if it doesn't converge to anything, Thomas? Then you cannot use this test, of course, right? Okay. If it's not convergent. Now, we may say it converges to infinity, but infinity is greater than 1, therefore it's divergent. Now, how about root test? Let me use another color, blue color, root test. Root test, strangely, has similar situation. The nth root of the absolute of the nth term. If this converges to L, then you use the same rule. Okay. If the limit is more than greater than 1, then it's divergent. Less than 1 is convergent. Exactly equals to 1 is inconclusive. Okay. But before I go on, I think I want to write some warning. I put it as a warning. You may want to write this down. Warning. Be careful with the requirement. be careful with the requirement. In limit comparison tests, okay, in limit comparison tests, A sub n over B sub n converges to L, which is positive and finite, implies the series A sub n and B sub n have same convergence. Either both of them convergence or both of them divergent, okay? Where the limit doesn't have to be greater or less than 1, but it will tell us if they are both convergent or both divergent. However, for ratio test, root tests, the limit has to be less than 1 to be convergent, okay? Now, furthermore, if ratio test gives L the limit equals to 1, which is inconclusive, okay, then root test will also gives L equals to 1, which also inconclusive. In fact, there will be if and only if. So let me update this. It will be if and only if. In other words, if you use root test and it gives you inconclusive, then ratio test will give you inconclusive too. Okay. Now, I will take a little break. We will come back and do problems from here. Okay. We come back, we'll do problems from here. Let's take a 10 minutes break, 5:35. You can see some examples in our textbook about this ratio test and root tests. Now, root tests usually done when the terms has exponent n, while ratio test being done if it has factorial and also the power of n. Let's say, for example, you can do problems from the examples though. Okay, but suppose I use number 8. Number 8, we have the sum of n factorial over 100 to the n. N equals to 1 to infinity. Well, this is a positive terms, right? This is a positive terms. And then this is a positive terms. And so it will be either divergent or absolutely convergent. It won't be conditionally convergent because this is not alternating to start with. Okay, and then suppose I want to apply a ratio test. Okay, so the absolute of the n plus first term over the nth term equals to n plus 1 factorial over 100 to the n plus 1 big over n factorial over 100 to the n. I ignore the absolute sign because it's positive anyway. Okay, and feel free to skip that step and go ahead to this step. So basically, the n plus first term multiplied by the reciprocal of the nth term. And then I go on further. Notice that this guy cancel this guy to be over 100, right? while n plus 1 factorial is actually n plus 1. That's actually n plus 1 times n factorial. So the n factorial cancel with that one, and I end up with n plus 1. Now this converges to what? When n goes to infinity, this goes to infinity, which is greater than 1. Right? So this series is divergent. Okay, little note. If you think about the nth term, n factorial over 100 factorial, this term itself is actually convergent to infinity. Why? Because this is n times n minus 1 times n minus 2 all the way down to 1 over 100 times 100 times 100 times 100 all the way to 100, like this. Right? Now, which is this is actually greater equals to n over 100 times 1 over 100 to the n minus 1. Okay. Actually, I want to say to the 99. The 99. Okay. And the thing is, this guy here goes to infinity when n goes to infinity. You see what I mean? When n is anywhere between 1 to 100, this a sub n is less than 1. This is less than 1 for n less than equals to 100. Okay, but starting from 100, 101, 102, 103, then this part here will be greater than 1, and this becomes a fixed constant. It's very, very small, but fixed. Okay, now this guy here will go to infinity. Okay, so because this a sub n converges to infinity, then by divergence theorem, or by divergence test to be more precise, not divergence theorem, by divergence test, then the series is divergent. Okay, so that's another reason that this series is divergent. But what I want to show you here is the ratio test. Do you want to pick other question? Maybe. Let me ask you to ask me 3 questions from this section, up to number 29. Maybe 4 questions. You tell me what you want me to go over. The reason I asked you to do this because later on, if you say that, Thomas, you never do that problem, then I will say you never asked that question.
Professor, could we do number 16?
Number 16. Any else?
I'm looking at my book right now. Let's see. What about What about one of them that's out written as a series, like 21,
Number
where
21.
it's written out sort of, sort of already written
Okay,
for
number
us.
21. Any else?
I guess 17, because it actually has pi and a ratio and
17.
Am I looking
Are
at the
you in
right section?
11.7?
Am I in
11.7?
11.7?
11.6.
I'm in 11.6.
I'm looking at 11.6.
Wait, am I looking at? Oh, I'm looking at my 8th edition. I'm sorry.
Okay, then read your question. Maybe they're the same question.
Probably 17, 11.6 is infinite sum from 1 to infinity cosine n times pi over 3.
Oh, okay, for it's number 19 for us.
Oh, okay, over n factorial.
Mhm.
Yeah, I have a digital copy as well as a physical.
Okay, let's try number 16 first. So number 16, we have the series 3 minus cosine n over n to the power of 2/3 minus 2. And this is n from 1 to infinity. Okay, the thing is, I don't think I need to use root tests or ratio tests. Do I want to use root test, ratio test? I don't need to in this case, actually. Yeah, okay. I will do the following. Solution. Consider the series of absolute value. Now, notice that for the first couple terms, it doesn't work really well because when n equals to 1, this is negative. Right? When n equals to 2, this is less than 2. Right? Okay, so let me do maybe 4 instead. Start from 4. Okay, well, you know what? Go back to 1. Go back to 1. Go back to 1. I want to say that this is equal to the first term is 3 minus cosine 1 over negative 1 plus the second term is 3 minus cosine 2 over 2 to the power of 2/3 minus 2. Okay. Plus, I think the third terms we are okay. 9 to the power of 9 is greater than 2. Okay, so n equals to 3 to infinity of 3 minus cosine n over n to the power of 2/3 minus 2. Is it okay so far? So the first two terms I write it up. Okay, so let me call this the first term. Of course, that's finite. The second term here. Okay. Now then, the last term, this guy here, I want to bound it above. Now notice that what is the upper bound for the numerator?
Is
What is
it
the
3
upper bound?
over n to the 2/3?
Repeat again.
The 3 over n2. Is the cosine the alternator or?
No, it
Oh, no,
doesn't
no.
alternate it. It doesn't alternate it.
Mhm.
Yeah,
It's
but we
just
know cosine is
one.
between -1 to 1, right?
Mhm.
So 3 minus -1 or 3 minus 1, it will be between 2 to 4. So I can bound it above by 4. I can bound it above by 4, and then this is n to the 2/3 like that. Oh no, this seems to be, but the bottom one is actually will be divergent though. The bottom one will be divergent. So let's bound it below instead. I want to bound it below instead. See this guy here, I can bring the 4 out, right? So according to my scratch work later on, I can bring the 4 out. Right? But this will give me a P series where P is 2/3. Right? Okay, so let me change strategy. I was expecting that to be divergent, to be convergent, but apparently it's not. I start seeing it better. This is bounded above by, so the lower bound for this is 2. Boom. Okay. In fact, I can say this, I can bound it even further below by this. Right? Let me bring the 2 to the front. Okay. And we know that this is, P series, P equal to 2/3, which is less than 1. Okay. So this is divergent. This is divergent. But because we bound that below by something divergent, so this series here is divergent by see, I bound it below by something divergent. So that series here, this series here is divergent by
Comparison test.
Comparison test. Okay, so what happened to the original series? The best we can say right now is it is not absolutely convergent. Not absolutely convergent. That's the best we can say. Okay, now then the thing is it convergent? Is it conditionally convergent, or is it No, the thing is, this is not alternating though. This is not alternating, my bad. Even without absolute value, I'm fine. So not absolutely convergent now. Okay, so I want to show that this is not even. This is not even. It's not even conditionally convergent. Okay, so now I will treat that without absolute sign. So I went to a wrong direction since the beginning. I really thought that this is convergent in some sense earlier, but apparently it's not. Okay, now this is equals to the first term plus the second term plus the third term I start. Notice that my argument is still, the argument that I use above is still apply even without absolute sign. Notice that this is greater equals to the first term plus the second term plus the summation on the top here is 2 over n to the power of 2 third minus 2. Right? And it still even work for which is divergent by P series. P is 2/3. So by comparison test, this series, the original series, is divergent. Okay. Now, what I'm trying to say is, remember I said earlier that we have some problem with this thing here. With this thing here. Okay, let me go back down. Go back down. I need to show it's either divergent, conditionally convergent, or absolutely convergent. Now, originally, I thought that it's absolutely convergent. Okay, so I tried that one. Now, notice that if I cut all my work here, let me use this color. If I delete all of this here, all of this up to here. Okay, so I just start here. I just do this. I'm actually done. I don't need to do it. This is all I need to do. Okay, the one that I put braces, you don't even need to show it, because all I did there is like I showed that it's not absolutely convergent, but it doesn't mean it is convergent. It doesn't mean it is not convergent. Okay, it doesn't imply that it is divergent directly. It's just not absolutely convergent. Okay, so once I show this, it means maybe convergent or divergent. Okay, it's just not absolutely convergent. Now, apparently, when I try to do my work earlier, in between, I pick up some idea. Hey, you know what? I don't need that absolute sign, right? You notice that? I don't need that absolute sign. My inequality is still true. So I can use that idea to show that it is still divergent, even without absolute sign. Okay, that's for number 16.
Professor, sorry, really quick. So how come we started at n equals 3 again? Because the denominator would then be positive, but what does that have to do with?
Oh, Why I need to start from 3 instead of from, because you see that when n equals to 1, the denominator is negative. You see, the denominator is negative.
Oh, so that's why we would need absolute values for the first few terms? Or
For the one up there, maybe I use absolute sign here to make it better than, because my A1, A2 here looks the same with the one at the bottom. But I just try to separate it from, I just want to say that my inequality applies starting from n equals to 3. So for the first 2 terms, I just make them equal. So this expression that I have here, okay, is greater than this expression, right? That's what I want to say. But it's greater not because the first 2 terms, but the terms after 3.
okay, thank
Okay.
you.
Mm-hmm. But I don't have any way to actually find the lower bound for the first 2 terms, so I just write them equal to whatever the terms are. Okay. Now let's come back here. Now notice that the first 2 terms here, I have no way to bound it above or below. In fact, the value will be negative, so I cannot bound it below by something positive, right? But I know that my inequality will start working well when n equals to 3. So the first 2 terms, well, where my inequality doesn't apply, I just copy paste whatever those 2 terms are. Okay. Now that's for number 16. Let's see more. What else? Number 19. Number 19. We have the sum of from n equals to 1 to infinity of cosine n pi of 3 over n factorial. Let's do by ratio. Well, because I know this guy here is, the absolute value of this is less than 1. Okay. But this one, this guy here, grow really fast to infinity and make the sequence goes to 0 super fast. So I will apply ratio test. By ratio test. The absolute of the next term over the current term is equal to the absolute of cosine n plus 1 pi over 3 over n plus 1 factorial times the reciprocal of the current term I know this will give me n plus 1 here. But I honestly don't know how to handle this guy. I don't know how to handle this. I don't know how to handle that. Let's see. I know at least it's 1 of n. And on the top, that's cosine n pi over 3 and then plus pi over 3. I wonder if there's anything I can do with that. Now the thing is, the bottom may be 0. That's the one I don't like. You see what I mean? The bottom one may be 0, and this will make the ratio to be exploding at some point, at some end, go to infinity at some end. I guess that's not what I really want to do. Let's check the absolute convergence right away. Consider, yeah, I think checking the absolute convergence is a lot faster. Yeah, because the top will be bounded above by 1, right? This is equals less than equals to 1 to infinity of 1 over n factorial. Then I will use ratio test for that one. By ratio test, absolute of the next term over the current term. So I apply that ratio test on this. Okay, that's equals to basically, eventually you will see n factorial over n plus 1 factorial, which is 1 over n plus 1, which converges to 0, which is less than 1. So this series here is convergent. And by ratio test, right? And then therefore this series here is convergent by comparison test. Therefore this series is the one without absolute sign. This series will be by definition, that's absolutely convergent. And therefore convergent. Okay, that's for number 19. See, earlier, I think my mistake was I tried to fit that into ratio tests or root tests without thinking more about the series that I'm dealing with. Right? That's my mistake, the mistake I made earlier. The reason I spent unnecessary steps earlier and they kind of like get stuck, because I tried to fit that into one of the tests, but if I see that series a bit further, I realize, hey, you know what? I can bound it above first, and then I use ratio tests. Okay, that's for number 19. How about number 21? The series of n squared plus 1 over 2n squared plus 1 to the power of n from 1 to infinity. And solution by root test. The nth root of the absolute of n terms will be equal to the nth root of n squared plus 1 over 2n squared plus 1 to the n. That's equals to n squared plus 1 over 2n squared plus 1 divided by n squared and this convergent to one-half. Don't use equal sign. No, don't use equal sign. Okay, what happened here, I actually deal with the algebra, but not dealing with the limit yet. Usually we're supposed to put limit, right? So if you don't use limit, okay, if you don't use limit, fine, but don't use equal sign here. Okay, use this notation to express then if we use the limit. Now, which is less than 1, right? Okay, this is usually, that notation means when n goes to infinity. Or you can also write it here as n goes to infinity. Okay, now then, so what happened to this series? And this series is absolutely convergent and therefore convergent. Okay, now let me ask you to pick 2 more questions. How about number 26 or number 24?
What's the limit of, what's the highest number we could go to for the questions? Like, from what range?
What do you mean?
Like, say for example, like homework wise, like what would it be?
Oh, homework.
'Cause I don't want to choose. I don't want to choose a question to go to, like an example, and it's something that's not going to be assigned to us.
I think for your homework, I will assign you up to number 29. Yeah, maybe number 29.
Could we try to do maybe
Number what?
30 or I'm trying to see because I see the ones without the series.
Without the series.
And that one looks kind of intimidating to me, but maybe it might be something simple.
Yeah, let's try to do number 30 then, because number 30 is actually similar to a lot of problems prior to that, like similar to number 27, 28, 29, right? In fact, number 29, number 27 are actually a special, those are special, it gives special value later on when you go to differential equation, I think. Yeah, let's try number 30. Even to write the question takes forever. So this is -1 to the n of 2 to the n times n factorial over 5, 8, 11, all the way to 3n plus 2. It has factorial. So let's do root test. By root test, no, I should, ratio test. Yeah, it seems to be intimidating, but then sometimes it's just about how patient you are in writing your thing, your rotation thing. Okay, so this is equal to all the terms are positive except the alternator, right? Okay, so I will just get rid of that absolute sign. I will omit the absolute sign, but at the same time, I don't use the alternator. Okay, so I will get 2 to the n plus 1 times n plus 1 factorial over 5, 8, 11, up to 3n plus 2 times 3 times n plus 1 plus 2. Okay, multiplied by the reciprocal of the current term, 5, 8, 11, all the way to 3n plus 2 over 2 to the n times n factorial. Okay, what happened to the 2 to the n plus 1 with 2 to the n? That will be 2, is it right? And then n plus 1 factorial with n factorial will give us
n plus 1
times n plus 1. Okay, and then I can actually cancel the whole thing here with the whole thing here, right? And I get 3n plus 5. I don't need parentheses. Which is 2n plus 2 over 3n plus 5 divided by n. That converges to 2 over 3 as n goes to infinity, which is less than 1. Okay, so then we can go back. So that series that we had earlier, that, you know what, I'm so effing lazy. You wish you use Microsoft Note to do your test. So this is absolutely convergent. Okay.
Thank you.
More questions?
Could we do number 24?
Number
Or
24, sure. Number 24, we have the series of 2n factorial over n factorial being squared from n equals to 1 to infinity. By ratio test. The ratio of the next term over the current term is 2n plus 2 factorial over n plus 1 factorial square times n factorial square over 2n factorial. You know, this is actually coming from 2 times n plus 1 factorial, right? That's what it is. Now, let's kind of like dissect this. On the top left, that will be 2n plus 2 times 2n plus 1 times 2n factorial. That will cancel with the 2n factorial underneath here later on. While on the bottom left, that's actually n plus 1 factorial times n plus 1 factorial. Let me slow down. While the one here, this is n factorial, n factorial. Then I can cancel this guy with extra 1 over n plus 1, right? And actually the same thing here. One and then n plus 1, right? Now then I get, oops. So I get 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. Divide the top and the bottom by n squared. That's equals to 2 plus 2 over n, 2 plus 1 over n, big over 1 plus 1 over n. You can FOIL that first and then divide by n squared, but I happen to see the pattern. So this converges to 4. Is that right? As n goes to infinity, which is greater than 1. So that series that series 2n factorial over n factorial being squared, which happens to be the series of the absolute value. Is divergent. Okay. Now it just happened that the terms in the original series is the same to if we apply absolute sign. So once we can show that this guy is divergent, then at the same time, because they are equal, then this guy also divergent. Okay, so notice I use the test for absolute convergence for the benefit of even if I don't need absolute sign.
So
Okay.
if there were to be an alternator in the original series, then we couldn't say that the original series is also divergent because it could be that it's convergent.
That's correct.
Okay.
Yeah. All you need to do is actually then, if you have alternator, right? So we know it's not absolutely convergent, okay? Then you just need to show that the positive part here is decreasing down to 0, which I don't think is the case. Yeah. I suppose so. Let's work on that hypothetical problem. So suppose on the other hand, we are dealing with the series of -1 to the n, just to get it alternator. Okay. Known from above. It is not absolutely convergent. So maybe convergent, maybe conditionally convergent, or divergent. Okay. So how do I know that it is conditional convergent or divergent? Actually, in this case, I want you to realize that if you check the limit for this, if you check the limit of that, I think it goes to infinity. You see? Yeah, I think it goes to infinity. Okay, let's try. Let's try. So solution. If it goes to infinity, then by divergence test, it's divergent. Okay. So a sub n equals to 2n factorial over n factorial square. Okay. This is 2n times 2n. Maybe I put it this way. N plus n minus 1, n plus n minus 2, all the way down to n plus 1, and then n factorial. That's for the top. While at the bottom, I have n factorial times n factorial. That way I can cancel this part. Boom, boom. Oops. That way I can cancel this part. Okay, now notice that at the top, I still have n terms, 2n times 2n minus 1 times 2n minus 2, all the way down to n plus 1, all over n times n times n times n. Right? But this is actually greater equals to 2n over n times 1 times 1 times 1 times 1. Okay. What I'm saying is this part here is more than 1. Right? It's almost 2. This is more than 1, almost 2. This is more than 1, almost 2. Slightly more than 1. When n goes to infinity, that's 1. But I know it's bounded below by 1. Okay? But then, to say further, this is equals to 2. Okay? Now, since a sub n is, it's always greater than 2, huh? There's no limitation what is the n here. So n, the n term is greater than equals to 2. So by divergence theorem, no, I say it again. I say it wrong again. By divergence test, not divergence theorem. Divergence test. This series is divergent. Okay. Other question? Let's try to do the question number 32, even though I don't assign that for your suggested homework later on. Let me write down the suggested homework first. Suggested homework from here, 11.6, number 1. Is it number 1? From number 1. Yeah, you can start from number 1 to number 29. But let's say, suppose I work on number 32. A series a sub n from 1 to infinity is defined by the equation. The first term is 1 and the next term is 2 plus cosine n over square root of n of the previous term. Determine whether this series is convergent or divergent. What do you think you will do? A ratio test. This is actually really nice here. This guy divided by that guy gives us this, right? So by ratio test, is equal to 2 plus cosine n over square root of n. Notice that I don't need to use absolute sign because this guy is greater than 1. This guy is between at most 3, at least 1, right? Okay, so I can bound this above by, I don't need to use absolute sign. In fact, I can bound it above by 3 over square root of n, which will go to 0 as n goes to infinity. Okay, then, so by ratio test, this series is absolutely convergent. Okay, aka convergent. That's for number 32. What else? Number 35. I think that's a good question. Number 35. For which of the following series ratio test is inconclusive? If you use ratio test, it is inconclusive. So part A for this series here. Is this series convergent or divergent?
It's convergent by P series.
Yeah, this is convergent by P series. P equals 3, which is greater than 1. Okay, but if you apply by ratio test, the absolute ratio of the next term to the current term will be n cubed over n plus 1 cubed, which if I divide by n cubed, I will get 1 plus 1 over n cubed, and this will go to 1. Okay. So you see this series we know is convergent, but when we use ratio test, it converges to 1. Part B. Actually, if you think about it, 1 over n, also the same, right? Maybe I put a note there. The series, the harmonic series, right? When you apply ratio test, we will get n over n plus 1, which is also converges to 1. Okay, so what happened here is you have two series, both ratio tests give us 1, but then one of them we know to be convergent and the other one know to be divergent, right? Okay, so I hope from here you confirm that if the ratio tests give limit 1, nothing can be said. You need to use another method. Okay, let's see part B. The series of n equals to 1. Infinity of n over 2 to the n. This one is convergent, even by ratio test. But y dot, then I will get n plus 1 over 2 to the n plus 1 times 2 to the n over n, which is n plus 1 over n times 1/2, which is convergent to 1/2. Dot dot dot, convergent to 1/2. So this guy is convergent by ratio test.
Could you also apply limit comparison test to this one?
Limit comparison test. You do limit comparison test to what?
Like to the original series, could we use that to test for convergence or divergence?
You say limit comparison test, so you need to give me
Oh,
another series, right? You need to give me another series that you know will work.
1/2 to the power of n.
1/2 to the power of n. I don't think that will work. Okay, by limit comparison test against the series 1 over 2 to the n. Here's the thing though. So if I do that, I will get n over 2 to the n over 1 over 2 to the n. That's equals to 1. Equals to n, and this goes to infinity. Nothing we can say.
Oh, okay.
Yeah, nothing we can say. Even if you reverse the order 1 over 2 to the n over n over 2 to the n, right? This will give us 1 over n. This goes to 0, right? Okay, but remember, limit comparison test, it's convergent if the limit L is positive and finite. If it is 0, nothing can be said. Remember that?
Yeah.
Right? If the limit is exactly 0, then we cannot say anything. In other words, limit comparison test against the series, this geometric series, is inconclusive. Is inconclusive. Apparently, in this case, seems like ratio test is the only way.
Is there any certain technique that would be like most general?
No, though.
No,
Each test is being designed to attack certain class of series.
okay.
Yeah, so there's no test that we can do that. Other question maybe? Oh, you know what? I'm not done yet. That's the only part B. So let me continue here. So limit comparison test is inconclusive. I think I should say against that series is inconclusive. So I hope you see that from here, you see that root test and ratio test, you basically compare it to itself. You don't need another series to compare. Now, comparison test and limit comparison test, you need to find another series that you will compare that to. You see what I mean? Okay, that's why when you say, oh, can we use limit comparison test, then I need to ask you, you need to test that against what? While if we use ratio test, I don't need to ask that question against what, because we basically ratio of the next term to the current term, right? Okay, now let's see part C. Let's see part C. The series of -3 to the n minus 1 over square root of n. This is infinity. Do you think this is convergent or divergent? Let's do ratio test first. That's what I want us to do by ratio test. By ratio test, then blah, 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 I will get -3 to the power of n over square root of n plus 1, square root of n over -3 to the power of n plus 1. I have absolute value, so I will get 3 times square root of n over n plus 1. Dot, dot, dot. This will go through convergent to, what will this converge to?
Three.
Hmm?
No.
Yeah, in total it will converge to 3, right? Okay, but the one in I circle in yellow there is convergent to 1. So from here we see, oh, by ratio test, this series is divergent, right? Yeah, this series is divergent. Okay, and then part D about the series square root of n over 1 plus n squared. This is convergent, right? Don't you think so? This is convergent. Because this is less than equals to this, which is the series like that, right? This is convergent by P series P is 3/2, which is greater than 1. Okay, now the thing is, if we use ratio test, will that be inconclusive? If I use ratio test, then I will get square root of n plus 1 over 1 plus n squared times 1 plus n squared over square root of n. I will get 1 plus n squared over n squared plus 2n plus 2, I believe, and then square root of n plus 1 over n. Now, this will converge to what?
1.
That will converge to
No.
1. Yeah, that's right. That's converge to 1.
Yeah,
Okay.
I accidentally added 1 plus 1, but no.
Okay, and how about this guy here? Converge to what?
1.
Also to 1. So basically, this series, if you use ratio test, you will get inconclusive. Okay, but therefore we need to use another test, whatever test we have available. Okay, now I believe I gave you the suggested homework already. There are more questions actually nice to do from here, but I don't think I would like to. Those are more into proving, and now I'm not into that. At least not now. Not now. Okay. How about number? If we go to 11.7, Thomas, are you sure you have only 14 minutes to do 11.7? Well, the thing is 11.7 is basically strategy for the testing series strategies. Or testing series. Let's collect all the tests that we have had. First one, divergence test. That says that if the terms not converging to 0, then the series is divergent. Right? Okay. And then second, we have integral test. Now, before integral test, let's do geometric series first. Geometric series. Usually by something times something to the n. Let's make it n minus 1 to make it clear, but it doesn't have to, as long as you have something constant to the n. Okay, something constant to the n. And this will be convergent if absolute value of r is strictly less than 1. It's divergent if the absolute value of r is greater equals to 1. Okay, that's for geometric series. And then from there we have what else? Integral test. Okay, so for a series that is non-negative, what else? Eventually decreasing. Then the series n, the integral of the continuous superposition function to infinity have both, maybe are both convergent or both divergent. Okay, in fact, from that integral test, we have the subtopic that the error, the remainder, I should say, the remainder, which is the error. The error, the remainder of, if you stop at the nth term, will be less than equals to the integral from n to infinity of that the continuous superposition function. Okay, we define the infinite sum to be the n partial sum plus the remaining part. That's the definition. Okay, so the error, the one that we didn't add, can be squeezed down by that integral. Now, the consequence of integral tests, is the P-series. Okay, the P-series, 1 over n to the P. This is convergent when P is greater than 1, divergent if P is less than equals to 1. In fact, when P is equals to 1, it has a special name. The name is harmonic series. Okay, now then, what else? We have comparison tests. But we can use comparison tests only for positive terms. Okay, so for A sub n non-negative, actually both of them, A sub n and B sub n, and the series A sub n is less than equals to the series B sub n, if the upper series is convergent, then the lower one is convergent. If the lower series is divergent, then the greater one will also be divergent. How about limit comparison test, which is actually the subtopic of comparison test? Limit comparison test for the terms non-negative. Okay, for non-negative terms, then the ratio A sub n to B sub n, if this convergent to L, which is strictly greater than 0, L not equals to infinity, okay, to finite L. Maybe I write it finite. Then the series for A and the series for B are both convergent or both divergent. Okay, we have similar case for the integral test. The next one, alternating series test. the series where we have alternator of Bn, where the Bn is the positive part. This is convergent when the positive part of the term is eventually decreasing to zero. Okay, eventually decreasing to zero. Then after that alternating series test, we have absolutely convergent. That says that if the series of the absolute value is convergent, then the original series is convergent. Okay, but be aware of this configuration: conditionally convergent and absolutely convergent. Okay, and to memorize that, you may prefer to imagine this Venn diagram in which we have convergent, and inside of that we have absolutely convergent. Okay, so once it is absolutely convergent, it must be convergent. But it is possible the series is convergent without being absolutely convergent. Okay, now continue from that. We have ratio test and root test. Let me just combine those two. Where suppose the absolute of a sub n plus 1 over a sub n converges to L, or the nth root of absolute of a sub n converges to L. Then the series is convergent if L is less than 1, divergent if L is greater than 1, inconclusive if L is exactly equal to 1. Okay, that's what we have learned so far. Now, we basically need to apply that ideas, what we have learned here. We don't know which test we will use into these problems here. Okay, so during this weekend, I would like you to try 11.7, number 1 to number 37. Do as much as you can. Okay, do as much as you can. And on Monday, I hope during the office hour, you can ask me some questions. And I think on Monday during the office hour, if you ask me question, I will record that so that we can present it to the whole class in case you miss that section. But of course, don't rely to other students, because if you rely to other students, it is possible nobody asked me question, therefore I don't have anything to record. Okay, yeah, that's for today. Monday I will do power series. I think that one will take some time. Yeah, I will do 11.8 and then 11.9 on Monday. On Wednesday next week, I will continue 11.9 and 11.10. Okay, the 11.10 can be done separate from 11.9. Let me see again just to make sure. Yeah. Okay, that's for today.
All right. Thank you.
You're
Thank you.
welcome. Mhm.
See you Monday.
Thank you.